So last time we talked about this convergence thing, but I just want to look at it really quickly and just kind of see the big picture. You know, our formal solution has this form involving the sine basis part and then the decaying exponential function. Essentially, you know, we want to think about, is it absolutely convergent? So we take the absolute value of it. And ultimately, when you look at the heat, this formal solution of the heat equation, it's really nice. And the reason I'm saying that is I want you to appreciate it now, because when we do the wave equation, it's not going to be this nice. And here, the heat equation, it's almost too nice, like it's spoiling us. You know, it's got a lot of very nice qualities. So anyway, one thing right off the bat, you know, that to talk about is, well, in terms of the series, this part here, the sine part, we can bound it by 1. So that's, you know, a nice quality. We can bound this by 1, no issues. And then if you look at the exponential part, as n goes to infinity, this thing goes to 0 really quickly, really fast, right? So, you know, these are all really good qualities in terms of wanting convergence. And so it really just comes down to this b sub n term right here. What is that doing? And so you remember from our Fourier series theory, you know, when you plug in t equal to 0, we get a Fourier sine series. So we know this thing is dependent on the initial condition f of x. It's like the integral f of x, I think 0 to L, and then there's a 2 over L out front, and then sine n pi x over, I know this is just like, you know what it is. I don't even need to do this. It's just me writing. I can do this. Oh, yeah. All right, I messed up. Okay, well, that's as good. Okay, so anyway, as you know, it all now depends on the term we would use is regularity of the initial condition, initial temperature f of x. Is that continuous? Is it piecewise smooth? What's going on with that part? And so, you know, as long as you don't allow f of x to blow up, that doesn't allow b sub n to blow up, as long as f of n is fairly nice so that we get the oscillatory cancellation so that the Riemann-Lebesgue lemma, you know, makes that coefficient go to 0 fast enough, we'll have convergence. You know, so essentially now that's all we've done here. So we just do the bounding. I've taken you know, the series term here and just bounded it term by term, getting rid of the trig function, dropping the absolute values around the exponential function because it's positive. And here I've gone ahead and assumed this coefficient in the front is well behaved, just to say, okay, well, if we assume it's well behaved, you know, what would happen? And so we're able to, and then here I was very analytic. So this part, this whole section, because I love analysis, so that's part of my issue. So I was being ultra analytic here. So here I just showed that the inequality is true for the partial sums, because the infinite sum is really a sequence, you know, it's a sequence of partial sums. So I show it's true for each term in the partial sum. And so then by definition, you can say one sequence is less than the other sequence, because that's what it means to say one sequence is less than the other sequence, is that each corresponding term of one sequence is less than the corresponding term of the other sequence. So here I show that term by term that the sequence satisfies the inequality. So then I get the conclusion I wanted, which is down here. One sequence is less than the other sequence. And so now I want to show this, you know, series / sequence of partial sums converges. And there, the only issue there is in the up here, this n squared term. So here's the index. Here we should only really worry about the index. And we're kind of, that's really the only, you know, not variable, but I would use the term parameter. And it's being squared. So it's not a bad thing, but we just want to analytically have a way of analyzing it using one of our tests or something like that. And so we want to just simplify that if we can. And so this is old numerical analysis trick. If n is greater than or equal to 1, multiply both sides by n. So it's a nice trick here. And then you get n squared is greater than or equal to n. And now I can multiply the missing term. And you know, every other term in that exponent is non-negative. Pi over L squared, K, our diffusivity constant here, time T is assumed to be greater than 0. Alana?
Yeah, can you just say one more time why sorry, it's kind of loud, my coffee maker's.
Oh, no, that's fine. No,
can you say again why in the Fourier coefficients it's 2 over L rather than 1 over L on the slide before?
Yeah. So it comes from, actually, Alana, it'll be on the homework that's going to come out this afternoon. So I really appreciate that question, and I'm going to let you sort it out on the homework. So great question, but if you just do the integrals, that's how it works out. One way to think about it, at least for the even case, this doesn't quite work out for sine, but if you think about when a function, like here it is for the regular Fourier series, in the case when it's even, you can go 0 to L and double up. And that's kind of sort of what happens here. But yeah, it's on the homework that I'm going to put out, homework 6. So yeah,
on homework 6.
Yeah, you're kind of foreseeing the future. So you're predicting what's coming up, which is good.
Because in homework 5, we also have to calculate those coefficients. So should we just have the 2 in there, like as part of the formula?
Like if you use orthogonality, it all works itself out. So we can talk about this in office hours maybe too. Okay.
Yeah.
So here now I'm going to multiply both sides by oops. Okay, here we go. I'm going to multiply both sides by this missing term, which is positive. And so then exponentiate it. So remember the exponential, that's an increasing function. And then take the reciprocal. And so now, here's where I had the typo. So here I forgot right here. So now I can bound the series that's bounding the series of the absolute values of our, formal solution. I can bound that series with this series right here. So I've got sigma n going from 1 to infinity, m times e to the minus pi over L squared. So last time I forgot this square right here. So I have publicly atoned for my error. And I've also put it on videotape for everyone in the universe to see. Anywho, now if you pull the old n out, so here I have, the index, then what we have here looks like the old geometric series. Be careful, it's not a full-on. So here, if we have the full geo series would be like this. Sorry, I have to talk about geo series because there's always like this little index issue with geo series. Okay, so in this case, because the series is starting at 1, if you want what you call a full geo series, we'd need the exponent up here to be n minus 1. And that's because if you actually, we should really think of a geo series as being this sum, A plus AR. All right, I'll write one more term and stop. That's really what we should think of as a geo series. So, and what do I mean by that? Well, the very first term is the term that should go in the top here of your sum when you write it out. And yeah, whatever's being raised to the n, that should be in the 1 minus r position, in the r part. So here, if you write out the sum, when n equals 1, the first term is capital M times e to the minus pi over L quantity squared kt. And so the sum looks like this. And before I had forgotten the squares. But the point is here, the thing converges And I feel like if we know it converges now, I can say something about the accuracy of the partial sum, right? So I feel like there's probably an error term buried in here too, since we can bound it by something that we actually know converges, and then we can approximate this geoseries. Anywho, so yeah, and here, the R is less than 1 because this exponential function is a decreasing one, the exponent's negative. So yep, we can conclude that the thing is absolutely convergent, because the series of the absolute values, if that converges, then the original series is absolutely convergent. And the only place where there's any possible issue is in B sub n. And B sub n comes from that initial condition f of x. So as long as we start out with, what we're here, not being too technical, just we start out with quote unquote reasonable data, piecewise smooth, something that doesn't have infinite discontinuities, then we'll be okay. And I should mention something. So here, let me mention it. Something, no. Suppose we do have a function with infinite discontinuities, in theory, I mean, we could make the series. It's just that the series may not converge. But what if we don't use all the terms? What if I still do a Fourier series of a function that has an infinite discontinuity, and then just use the first 10 or 100 terms or something? So from a maybe applied scientist point of view, we might be able to break the rules on that just for the heck of it, to see what happens. Why not? So yeah, so in general, if we have these nice initial conditions, we shouldn't have any issues. So then I just did a quick example here, and there's some little new stuff at the end here that I should show you. That's more kind of a numerical analysis than anything else. So here for this type of, PDE here, one thing I immediately notice is that we've got these trivial boundary conditions so that I can just do separation of variables directly to U. I don't have to break it up into transient solution and steady state solution. The steady state here will be trivial. So here, doing the usual stuff, you can show, we can solve the integrals, finding the Fourier series now is just about finding the coefficient, right? And they're always we're not trying to integrate too complicated functions in this class, right? So it's more the idea of it. And so, yeah, here we can come up with the formal series representation of the solution. Remember last time we've proven the formal series actually satisfies the heat equation, we verified it. And so here, I did an approximation using the first 8 terms for very small t, because here I want to think about the effect of the boundary conditions. We can interpret these things mathematically, but we can also interpret them physically. And here the boundary conditions are being forced to be 0 for t greater than 0. So I wanted to just take a look at that initial, just to see what exactly is going on. It's weird, right? The intuition is weird. And I mean, I think it's continuous across t. Then the limit as t goes to 0, it goes to the Fourier series, which converges to the function. So I don't know, something weird's going on here. So, okay, so we can talk about, now not using all the terms to approximate the temperature. And here, this is all about the exponential terms. So in the solution, we've got a sum of exponential terms, right? So here, the larger the exponent is, the quicker the term decays. So here we've cut off all the terms that are order 2 or higher. That is to say, when I'm looking at this, I'm thinking the wave, this is n equals 1. So sometimes we use like, the wave number we're using, this is like that first term, n equals 1. I'm not using n equals 2. Those you could, but here just as a starting point. And furthermore, you say, okay, Now, in addition, if t is big, then those terms are even smaller. So these are, small terms, small terms. So we just take that first term. And now we have kind of a easier function to work with, to now predict temperature. So here, then I just plugged in some numbers to actually, get, some graphs to plot. So here I'm going to now plot this graph right here for x between 0 and L, okay, for various values of t. So here we've got our spatial variable x, so that'll go between 0 and t. So I'll fix t. So I'll say, suppose t is, 1 second or 2 seconds, whatever. I'll fix t and then graph it with respect to x. So here we go. And you can check, what happens to the equilibrium temperature as t goes to infinity, right? We can verify our theoretical. I should have done them one at a time. I didn't animate that quite right. Sorry, folks. Took all the suspense out of it. So you see the starting temperature of 100. And then once time starts, the ends are immediately cooled. And you can see as t goes to infinity, as t gets larger and larger, the temperature decays, in this kind of, I don't know, orderly fashion to the equilibrium temperature of 0. So, it's like the math is sort of behaving like how we would hope temperature would behave. And in this case, you should think about why is the maximum at the center here, if the ends of the rod are being forced to be 0 degrees, that kind of fits the physical interpretation of what's going on. So, okay, so here's some further approximations to kind of, use the heat equation that we found to say something useful. So the question here is, how long will it take for the maximum absolute temperature of the rod to be less than 1/10 the initial maximum absolute temperature? So the word here, absolute, is to indicate that I'm just taking the absolute value of everything. So here, I want to find, first of all, it says how long. So I want to find a time so that the maximum temperature, so we're looking across the entire length of the rod, finding out where the maximum is and taking the absolute value of that, so that is less than 1/10 the maximum, temperature along the rod initially when t is equal to 0. So here we're going to time t equal to 0 and finding the physical spot along the rod, the x value, where the temperature, where the absolute value of the temperature is the greatest. Here, we're trying to find the time, how long it'll take that wherever the highest point is, the absolute value of the, the temperature to cool down to 1/10 the initial. So here, the trick is now, it's not, mathematically it's not difficult. We're just going to replace u of xt with the one term approximate, with the slowest decaying mode approximation, and then do the math there. So if I take absolute values here, I can bound the sine term by 1. So that's what this term disappeared. So I take absolute values. Right. So bound this by 1. So yeah, and so now I stick this. I'm gonna so now we have this term is bounded by that. So do you know how, so the way the max works is it's the least upper bound. So if there's any other number that's an upper bound, then this will be less than that number. And so here, essentially, we've shown this is an upper bound, is some upper bound. And so the max being the least of the upper bounds will be less than this upper bound. A little more analysis there. So now we can just solve this problem here. So I've replaced the max stuff because it's bounded above. And the right-hand side, we can solve it. We know what f of x is. In this case, it's very simple because f of x is just a constant. It's just a constant function, 100. So now we just have essentially, you know, a Calc 1 type little problem to solve here. So I'm going to multiply, get rid of the constant, take a reciprocal to get rid of the minus up here, and now take the ln of both sides. And so, as you know, ln of e to the whatever gets rid of the e, and here I have ln of 40 over pi. And remember, we're trying to find the time. So we're trying to find the amount of time it'll take to cool to 1/10 the initial maximum absolute temperature. So I isolate T, and you know, that's a perfectly good theoretical answer, right? If we know L, the length of the rod, then we can get a number out of this. So here, oh, I calculated this part. And I left that L squared in the K. And typically the L squared over K is used kind of as a unit, as a natural time scale for these type of cooling type problems. You know, so okay, folks, so that's the end of it. And you'll see on homework 6 some problems like this that involve the slowest decaying mode approximation. And so, you know, this would be an example of that. And yeah, so I'm gonna stop right here. And I thank you for your time.